Okay, welcome everyone to a new differential geometry seminar. Today, it's a great pleasure to me to introduce Anna Fino from Università di Torino, who is going to talk about special Hermitian metrics and suspensions. Thanks, Anna.
Thank you very much for the presentation and for the invitation. It's like that I am in Córdoba back, so I am very glad to give a seminar in Córdoba series. And the talk will be about special Hermitian metric and suspension of mapping torus. I will try to present some result about mapping theory, which include also as a special case in manifold and Sol manifold. And the result will be, the first part will be a work in collaboration with Theo Grancher and Misha Verbitsky. And then I will talk about more recent result with my student Beatrice Brienza. And this is more focused on generalized scalar structure. So let's start. And let's start with the definition of suspension or mapping torus. So we have a manifold, we have a diffeomorphism of the manifold, and we take the product of the manifold times the closed interval 0, 1. And we do this identification. So we identify the point P0 with the point P, the image of P by F, with 1. Okay, we construct in this way a new manifold. And the nice thing that the new manifold is the total space of a fiber bundle with fiber with base over S1 and fiber M. And the way how is constructed, let's say, this reaction, the projection, comes simply by the projection of the product of M times the closed interval 0, 1 to the interval 0, 1. What is the structure group of this bundle is very simple because it's just the cyclic group generated by the diffeomorphism F. That's the idea. And it's quite powerful, this way to construct new manifold. Another way to see the same manifold is as a quotient of the product M times R by an action of zeta. The action of zeta on the pair PT is just, okay, you take F, you just say the power of F and power, and on the same time you do the translation over the integer. And the new manifold, the new quotient that you get is exactly diffeomorphic to the previous one. One thing that one can remark that if you take the Langevin form on the cycle as 1 and you pull back, what you get in your mapping torus is a 1 form which is closed, non-vanishing and closed. Is if and only if, by a theorem by Tischler, that if you have a compact manifold, you can distinguish when it's a suspension or a mapping torus from the fact that the manifold has a closed 1 form which is non-vanishing. And these mapping torus include, in a natural way, both Near manifold and Sol manifold, because at the level of the algebra, you always have a closed 1 form, and this gives exactly a non-vanishing closed 1 form on your manifold. Here, for Near manifold and Sol manifold, I will also always mean compact case. So the quotient of, let's say, an idempotent or a solvable group simply connected by a lattice, by a co-compact discrete subgroup. Just one thing about lattice.
Anna?
Yes?
In the theorem.
Yes, the theorem by Tischler.
Non-vanishing is the same to us in any point or
No, in any point. In any point. Yes, yes. You
non-zero at any point. That's
in any point, yes. This is exactly equivalent. And this paper by Tischler is quite nice because he introduced this notion where he considered in the symplectic case. In fact, he the paper is more what happens if you take a mapping torus of a symplectic manifold, and then you get what you usually call like co-symplectic manifold. That's the way I introduce and improve this general result. Yeah, non-vanishing in every point. Exactly.
Thanks.
Welcome. Okay, for nilpotent is in some sense easy to have lattice because it's enough to have a rational basis, and then using this rational basis, you can construct a lattice, and this is the theorem by Malchev. In the solvable case, in general, there is no criteria, simple criteria. There is the minor necessary condition that say that the Lie group has to be unimodular, so the trace of the joint representation of the X is 0. Okay, this is, for instance, enough as a necessary condition if you take an almost abelian Lie group. In that case, the new radical is just abelian, but it's not enough in general for the solvable case. There is in solvable, let's say, not almost abelian. So in the case that the new radical is not abelian, and there is this paper by Garland, that's a paper in Annals in 1966, were introduced for other reasons, not only that, introduced this notion, strongly unimodular, that's implied the notion of unimodular, and what he asks is the following. Take the new radical n, okay? This is an important in particular, and then you just take the series and I, starting from the commutator, and so on. And what you ask, that the trace of that X is exactly vanishing on the quotient of this quotient of the elements of the descending center series. So restricted to the quotient of Ni over Ni plus 1. For instance, when the near radical is not abelian, this is quite strong. We'll see geometrically that it's unimodular and let's say strongly unimodular are quite different. Okay, now I want to very shortly say something about the formality of mapping torus. In fact, how to compute the cohomology of mapping torus. Here we just take, okay, graded algebra, commutative, together with the operator D, and we satisfy the Leibniz rule and D square 0, okay? This is what is called commutative difference graduate algebra. We shortly call CDGA. And the standard example is the complex of differential form on a manifold with a standard differential operator. One can construct the cohomology of that, okay, and take as operator 0. And then you have a new one, a new CDGA. You have also notion of CDA morphism, let's say, preserving the previous, the grade, and with a good behavior with respect to differential. And you say that such morphism is a quasi-isomorphism if the induced map in cohomology is an isomorphism. So this is quite, these definitions are in some sense quite natural. And then we can introduce the notion of minimal, essentially when A is a free commutative algebra generated by a graded real vector space. So everything is determined by this vector space. And if you have a homogeneous basis, essentially, for which the order, you have a well-ordered set, which is given by the degree. So we are saying here, if the degree of I is less than or equal than the degree of J, for E less than J, and the differential of Xi can be written in terms of terms which are involving Xj with J less than 1, the I, our I. The nice thing that every connected CDGA has a unique minimal model up to isomorphism. And one can talk about minimal model of a manifold, connecting manifold, just as a minimal model of the CDA of the differential form with the usual differential. Okay. Sullivan introduced the notion of formality. For instance, Kähler manifolds are formal, but other type of manifold are formal. In this way, we say that a minimal algebra is formal if you have a morphism of CDGA between what and what? Okay, between your algebra and the cohomology of the algebra, and this induces the identity on cohomology. So one say that the manifold is formal if the minimal model is formal. In particular, we know by the result of Hasegawa, because he computed the minimal model of an Hill manifold, that an Hill manifold cannot be formal unless it's a torus. But the nice thing about solved manifold, compact solved manifold, that there is in many examples which are formal. In the last part of the talk, I will talk a bit about formality in relation of generalized scalar geometry, because it's not known, this is an open problem, to see if in general, when you have a compact generalized scalar manifold, is automatically formal or not. This is completely open. So every time you have example, it's good to check if the formality holds or not. Okay. What about the cohomology of the mapping torus? That's nice because you can determine everything in terms of the action, the induced action of F on the cohomology. Because what happened that the cohomology of a mapping torus fits in this Excel sequence. So in the middle, you have the cohomology of the mapping torus. And then on the right, you have just the kernel, or what? The induced cohomology at the level of R cohomology minus identity. And on the left, you have the co-kernel of the same map. But of course, at the level, cohomology level, R minus 1. One first remark that one can do, that since the space KR is free, then this exact sequence splits. So the cohomology of the mapping torus, in fact, splits in these two parts. So if you compute the two parts, you can compute the cohomology. Of course, in general, for a mapping torus, the computation of minimal model is not a trivial problem, but there is a lot of study of that by Marisa Fernandez, Bazzoni, Vicente Munoz, whatever. They found some sufficient condition for having formality, but also condition for having non-formality. Okay. Now I will leave this formality for a moment, and I want to talk about balance matching, because it turned out that some balance, let's say, example in the almost a billion case, which gives so many, for example, can be viewed as mapping torus, or something which is in some sense quite rich. So let's first review a bit about balance. I will not say much, just a short review about that. So we have a complex manifold, complex dimension n, and we say that the Hermitian metric is balanced if we take the differential of the power n minus time of our form, omega. Here I confuse the form with the metric. This is close. D of omega n minus 1 wedge power is 0. Differential is 0. I want just to mention this nice property. This is due to Goudouchon. For a Kähler manifold, you have always this relation between the Laplacian D, the Laplacian D bar, and the Laplacian, the usual Laplacian D. with respect to differential the Starroj Laplacian. For the balance case, this is a if and only if. So for a matching to have that property. This type of structure were introduced by Michelson in the nice paper. The paper is quite nice because he essentially on a compact case, he given an equivalent condition that we use a bit currents also for the existence of a balance metric. So the Michelson showed that to have on your compact complex manifold a compatible metric, which is balance, is equivalent that you don't have any positive currents at degree 1,1, which is component of a boundary. So it cannot be written like, let's say, del S plus the bar S bar. This is del and the bar just are defined using the duality between forms and currents. This gives some abstraction in terms of complex some manifold of codimension 1. And for instance, you using that abstraction, you can prove that some manifold, is the only known abstraction essentially, that some manifold have no balance, like the product of two odd dimensional sphere, like Calabi-Ekman manifold. For instance, S3 cross S3, if you take the Calabi-Ekman's complex structure, has no balance metric, but is, for instance, completely open to see if S3 cross S3 has other complex structure for which you have a balance metric or not. That's completely free. So this is only for specific complex structure. There are many examples. The twistor space or 4-dimensional manifold, Riemannian manifold, dimension 4. You need the extra condition that the metric is anti-cell dual. That essentially gives that the natural complex structure is integrable. And that's, you have automatically canonical way to define a balance metric. This is due to Michelson and dependent by Goodson. But there is also construction, a way to construct compact balance manifold using the bimeromorphism, starting from Keller case. So this was done, these are all papers, now old, by Alessandrini and Bassanelli, and essentially include, if you start with a compact Keller manifold, and if you start with a projective manifold, and you apply this bimeromorphism, then you get a Moisson manifold. If you just apply bimeromorphism to a compact Keller manifold, you go to Fujiki class C. And then in terms of, let's say, Lie group, there is a nice way, just start with a complex Lie group, which is unimodular, and just take any left invariant there, and then give a balance. And then there are more sophisticated construction due to Li, Fu, and Yao. And here they start by Calabi-Yau manifold, and they apply what is called a conifold transition. So that means that you contract special type of rational curves with special normal bundle. So you get something singular with double point, and then you smooth your double point. And then there is this nice paper by Giussi and Podestano recently. This is nice because I will not mention, but if you take a real compact Lie group and you take the Samuelson complex structure, this cannot be balanced. We show that in a paper with Granchero and Vezzoni. But the non-compact case, at least a simple case, to be of inner type, it just means some condition in terms of the symmetric space. It's just a decomposition. In that case, they show that you have balance. And as far as I know, they show this result in the simple case for a simple Lie group of that type. It's not known, I suspect yes, that this is in fact true for also semi-simple case. Okay. I just mentioned very quickly some results. Maybe I forgot some of them. But anyway, the first classification, of course, everything I didn't mention, for n equal to 2, the condition just give Keller, right? So the first complex dimension that is interesting is the complex dimension 3. And an important case, there is a classification on the level of Lie algebra by Ugarte. And then the 8-dimensional case, still important. There is a classification by Andrada and Villacampa with the condition that the complex structure is abelian. So the space 1, 0, the algebra 1, 0 vector is abelian in this case. Then with Fatale and Ugarte, we consider the case of a solvable Lie algebra, which admit holomorphic 304. And more recently, with my student Paradiso, we consider first the case of almost abelian. So in this case, we have, let's say, a codimension 1, abelian ideal, that here I denote by H. We got a classification of, in this cise, with 9 isomorphism class. I am not going to say what are. And more recently, we consider the next step, which is to consider almost nilpotent. So H before will be not anymore abelian, but just nilpotent. And we get extra 8 classes. So 8 plus, these are extra with respect to the previous one. Here, I want to mention some construction coming again by, let's say we start with something which is hyperkähler, and we arrive with something which is non-Kähler, okay? Why we consider this type of construction, I will say in a moment. This comes from a paper by Quinn and Wang, where they construct some compact manifold, complex dimension 6, which are complex, and they are in the same time diffeomorphic to complex Calabi-Yau. So what I mean here for complex Calabi-Yau just means that the holomorphic bundle is trivial, okay? And on the same time are also diffeomorphic to symplectic Calabi-Yau. So here in the sense that you have a symplectic structure, you have an almost complex structure, and then you take the first chain class of the almost complex structure. In that paper, they didn't consider anything about metric, just construction and property, topological property. So the question that we study with Grancher and Verbitsky is, okay, which type of metric they can have? And we try, the first try is, okay, let's see if they have balanced metric. And the answer will be yes, okay? Now I explain a bit the construction of Quinn and Wang, and we'll see how we generalize. Instead of considering the Kummer surfaces, which is in particular a special type of hyperkähler manifold, we'll consider a general hyperkähler, and we'll see how it's related to the mapping torus. So the Kummer you can see in many ways. The more simple way, maybe, the type of K-free surface, and the more simple way is, okay, let's take the torus, the complex torus, which I denote by T2. So let's call Z1 and Z2 the coordinate on Z2, on C2, okay? And just take the involution given just by minus identity, essentially there. This give a map on the torus, and we just take the quotient of that, okay, with the group generated by the involution. Is not anymore smooth, the manifold. You have 16 double points, but are simple as a singular point, so you can get something smooth just doing the blow up of your point. You can see also in another way. You start with the torus, you blow up, and then you do the quotient by the involution. You get the same space. Okay. What we have here essentially is not it's not too much important that the fixed point is, as I say, the union. P1 are just a copy, right, associated to the blow up on any point. But what we are interested in here is the second part of the remark, because if we take the 2-0 form, the standard one, let's say, this is always induced, okay, is inducing a nowhere vanishing 2-0 form on the 2 torus. And then we will take the pullback. We will have a holomorphic 2-0 form. So in our Kummer, we have Keller plus holomorphic 2-0 form, which is equivalent to have an hyperkeller structure, essentially. Now let's go to the mapping torus part. And let's see what type of diffeomorphy we can construct. If we take a matrix like that with determinant 1, coefficient in zeta plus I zeta, okay, we have this condition on the trace, on the modulo of the trace. This is a condition that ensures what I will call later the hyperbolicity of the induced diffeomorphy. And this is something that makes the manifold non-killer, essentially. Then we take diagonalizable with 2 eigenvalues, and denote by dv1, dv2, they associate eigenvector on the induced map on the first cohomology, first complex cohomology. Then what we have? We have that the map is preserving the 2-0 form, is preserving the divisor, and what I define, that's what we want, a transformation on the Kummer that is not preserving any metric, in fact. Is only preserving the complex structure, so it's a holomorphic transformation. And the important thing here that is preserving the induced holomorphic 2-0 form. So this in particular implies that it's preserving the volume induced by that. We can work now on the product T2 time R time S1 and take the action induced by A in this way. So what we are doing on the point P of T2, we work with this map A, let's say. Then on the same time, we translate X by 1, and we don't do anything on Y. So what we have is an action on what? On the product of the Kummer times R time S1. And this is exactly the manifold that I call here AKM, because it's constructed by the Kummer, considered by the 2 guys that I mentioned before. And it turned out that by construction, the canonical bundle is trivial. Okay, now we see a bit more general what is going on. So let's start with a compact Keller manifold. Let's take an automorphism that preserves the complex structure. And we'll say that this is hyperbolic in the action on the 1-1 cohomology, DL1-1 cohomology, is doing the following. As a unique eigenvector or eigenvector with lambda unique, essentially, lambda bigger than 1, such that the pullback under eta is lambda eta. This is actually the condition to be eigenvector, essentially. So we can generalize a bit what we saw before. We take an automorphism, which is hyperbolic, the compact Keller. We take a lattice in C. Let's suppose that it's generated by Psi1 and Psi2. And then we take something which posteriori will be a mapping torus times S1. You see, because we are acting on P, point on M with F, and we are translating essentially zeta with Psi1 and Psi2. And what we can say about that, we can say the following. That's the first thing. If we have not only Keller, but we have also a holomorphically symplectic structure, so that means essentially that is hyperkeller. And F is preserving, is hyperbolic in the sense that I wrote before, but is also preserving the holomorphic symplectic form, then one can construct a new manifold, complex manifold, as I described before, And this is a balance metric all the time. I don't want to be technical and to prove how we construct the balance metric. This is an existing result. So we use essentially currents, but we use essentially the fact that our manifold project over a complex curve, that in this case is just a product S1 cross S1. And the only thing that we check is that this projection, this map, is essential in the sense of Michelson. This is some condition involving the applet class that I am not going to be because it's a bit technical. But what I want to mention, that if you apply the previous construction that I saw before, that I described before, in the case of the real four torus, so you just say the same map, A, like before, then the suspension that you get is almost a billion. Oh, here I leave compact Sol manifold. I mentioned before that Sol manifold, I always mean compact in this context, but anyway, and it turns to be balanced. For this case, you can explicitly write the balance metric because everything can be described in terms of the Lie algebra, the group, and so on. But it seems we are trying to understand better. The previous result is an existence result. We don't have an explicit expression of the balance metric even for the previous example constructed by the Kummer. So it would be nice to find a way. This is nice. We have an existing result, but it would be nice to have in general a way, even for that example, to write down explicit map. Why? Because we would like to study, for instance, the Alstrominger system related to this new example and so on. Here I mentioned some interplay with other complex structure, type of metric that you can have compatible with the same complex structure. One notion is what is called SKT or pluriclose. I will go back later about that. This is just a condition on the Kähler form to be DD-bar close. And with Luigi, we conjecture this is still open. And we'll see in a moment that even in this construction that I mentioned before, that is a bit complicated, but one can show again that that example, which is balance, cannot be SKT. We'll see how. I will just say a few words about that. Anyway, the condition DD-bar omega 0 seems to be really combined with balance. So you have two different metrics compatible with the same complex structure. Seems to force all the time to be Kähler. But this is not true if you ask, instead of omega to be DD-bar close, you ask omega n power n minus 2 power to be DD-bar close. This is, we construct an example with Granchero and so on in a paper. And the example is homogeneous, in fact. It's an homogeneous example. I want just to mention why it cannot be SKT or pluriclose. We prove, in fact, something more stronger. We prove that you cannot have any metric omega such that DD-bar of the p power, so omega p, is 0. Cannot be that. And the way is again using currents. So essentially using the duality is enough to show that the suspension has a current of type EP, which is strongly positive and DDC exact. I don't want to mention the proof, but the nice thing here is that it's using the condition in a strong way. the condition that I write before for the hyperbolicity of C, because you have these eigenvalues, lambda. And then you have also eigenvalues at the level of cohomology on the 2p cohomology. This is a result by Bogomolov, Kamenova, Liu, and Verbitsky. But then what we can see is that using the notion of mass, you can construct a new current as a limit, a current, which is preserved by F. Not really, you don't have F star sigma equal to sigma, but it's given by lambda sigma. And then nice, because then you can just take M times R, and T is a coordinate on R. So you have a new current, which is given by lambda minus T sigma. This is preserved by the action, as we define. So it's giving a current on S, and then you just take the DDC of that current and give you the obstruction, essentially. So for P equal to 1, you just get that your manifold is not SKT. So again, the conjecture is confirmed, is also in this case. Okay. Let's go now to the part that I want to present. This is, let's say, is a bit transversal of what I said before, because the conjecture is still open. For SKT or pluriclose, I just mean that the omega in this case is DD bar close. The same condition can be viewed in terms of the bismuth connection. The bismuth connection is just the unique connection that preserves the complex structure and the metric, and such that the torsion, you identify the torsion, the 1, 2, and 2, 0 tensor. And the condition to be SKT is just a condition for the torsion to be closed. That's exactly the condition. Again, here the complex dimension 2 is not so interesting from the point of view of existence of SKT metric, because it's always true that the compact complex surfaces as a SKT. And this is a good shown result, essentially. Okay, here I mentioned some previous result on at the level of Lie algebra. The characterization on the nilpotent case is due to Arroyo and Nicolini. I am not going to talk about that case. I will focus more on the solvable case. With my student, we study the almost abelian case, and we use a characterization by Romina Arroyo and Ramiro Lafuente. And essentially, we found out the classification of this 6-dimensional Lie algebra, almost abelian Lie algebra, which has a SKT structure. We describe a bit more, but here I want just to mention that. Of course, the almost abelian case is a special case or two-step case. And the classification in the two-step case has been obtained in dimension 6 by Freibert and Swan with a different technique, which is called share construction. More recently, with Fabio Radiso, we consider also the case almost nilpotent. So the nil radical is not anymore abelian, but is codimension 1. We suppose that. And the nice thing, unfortunately, would be nice to have a more geometrical proof of that. But if you impose, okay, here we also impose strongly unimodular, which is the necessary condition to have a compact quotient for the corresponding group to have compact quotient by lattice. What we show is that either you go back to the almost abelian case, or the dimension of the commutator of the new radical is 1. That means that the new radical is essentially an extension of the Heisenberg group. And in this case, we have again a classification. Here in red, if I am not mistaken, I put the one which are decomposable, like before. I forgot to mention. But the thing here that I still do not see geometrically is you can see from here that at least in dimension 6, you have that. I am trying to understand if this is a property also in higher dimension and how is it related. Can be that you see it's like for two-step, for nilpotent, this implies two-step, right? And here you have something like that, which is more general, but I still don't know why. I think there is some more to do on that. Now in the last part, I think I still have 10 minutes. I want to see how SKT is in fact one of the ingredients of more general geometry, which is called generalized scalar geometry. So let's give the definition of generalized complex structure. This type of geometry was introduced by Hermitian. It includes complex geometry and symplectic geometry as a special case. So instead of working with the tangent bundle of M, we work on the direct sum of the tangent bundle and the cotangent bundle. And so essentially here we can define the generalized complex, we generalize the usual complex. Okay, this subbundle E, you have to think that analogous for a complex structure is the bundle of 1, 0 vector, essentially. So here you work with a subbundle on the complexification of the tangent bundle plus the cotangent bundle, and you have two conditions, the three conditions, in fact, that E plus a conjugate give all the complexification of the tangent bundle plus the cotangent bundle. Then you have the closure with respect, okay, for the usual complex structure, you have the bracket, usual bracket. Here you have the Courant bracket. And then you ask that E is isotropic with respect what? You have a natural pairing, right, between tangent, a cotangent, and this gives you this metric that is neutral, in fact, metric. And equivalently, you can see a generalized complex structure as a complex structure on the bundle given by the tangent plus the cotangent, which is integrable with respect to the Courant bracket. This is another way to see the same thing. Here I just you can see why complex and symplectic are included as a case. And here I just describe what is the E, the subbundle, in the two cases, in the language that we wrote before. Okay, let's go to the definition of generalized scalar. This was introduced by Hermitian himself, but then Gualtieri wrote a very nice PhD thesis related to that. Essentially, we have a pair of generalized complex structure we commute and are compatible with the previous indefinite metric that I described before. And then we have this extra condition. This is a stronger condition. You have this bilinear form given by minus, then you apply J1, J2. Combining this way is positive defined. And what is the relation with SKT structure is that this was shown by Gualtieri. To have a generalized scalar is equivalent to have a pair of SKT structure in this sense. You see the metric is the same, and you have a pair, complex structure, let's call J plus and J minus. And what essentially here we are asking in the language that we saw before, that the bismuth connection related to the two Hermitian structure, the torsion of these two bismuth connection is the opposite one each other. And therefore you have the closure of the torsion because you ask for SKT condition. Here we have two types of generalized scalar structure that we can distinguish and give also consequence on the geometry of your manifold, let's say. because you have a case when J plus and J minus commute. So you have a natural involution, it's just the product, the composition of J plus and J minus. And then you have a natural splitting of your tangent bundle in the two angle spaces with respect to 1 and minus 1. For the first case, interesting case, which is the case of complex surfaces, there is, these are described, the GK, split GK case is described by Apostolo and Gualtieri. And here we go back again to Sol manifold, because one of them is a special type of Fino surface. Type SM is just depending essentially on the fundamental groups, so on the type of lattice, if you describe that in terms of Sol manifold. This was identified by Asakawa. The non-split case is much more richer and much more mysterious because this is the case when essentially, if you take the commutator J plus and J minus and you combine with the metric, you get the real part of what is called a holomorphic Poisson structure. I don't want to talk about that, but if that tensor that I say is, let's say, invertible, then you have what is a symplectic form taming a complex structure. And here, for this, there are still a lot of problems, let's say, because there are no non-killer examples for that case. Okay, in the last part, I think I have 3 minutes, is correct? Yeah. I will talk about what is known about generalized scalar structure on near manifold and Sol manifold. Okay, the generalized scalar, if you don't impose generalized scalar, but only generalized complex, near manifold are quite rich. Every 6-dimensional in manifold is a generalized complex structure. It's not true in dimension 8, but by Cavalcanti, they cannot have invariant generalized scalar structure unless they are tall. For Sol manifold, I wouldn't say that the situation is so rich, but at least you have examples which are non-killer. The first example is the Nova surface that I mentioned. Then I construct other example with Adriano Tomassini and Fabio Paradiso. So there are, let's say, but we want to describe which are. We want to understand if they are formal, whatever. In real dimension 6, with Fabio, we have a classification. But in this case, you have only split. So all the case have J plus and J minus commuting. So one can ask, okay, what happened for the solvable case? Can you have a necessary almost abelian? The answer is not. At least in unimodular case. We construct an example with Fabio that is generalized scalar, but is not strongly unimodular, and the example is almost important. What we can say in general, we didn't solve the complete picture in dimension 6, because we know that SKT implies the dimension of N1 equal to 1. But then we have 3 possible geometrical situations, let's say. The N1 is a line, and also the orthogonal complement of N is a line. So when the 2 lines do intersect, or J and 1 intersect N, then we can say that there is no generalized scalar structure, but it's still missing the other case, when it doesn't intersect that line and it doesn't intersect N. We don't know what is the case in this case. But then we found out, okay, in fact, the non-split is possible. At the beginning, I was thinking, okay, it cannot be. We found out an example in dimension 8 with Paradiso. And later with another my student, Beatrice Brienza, we realized that let's say the Sol manifold that we got in dimension 8 is a suspension, is a mapping torus of a 7 torus, and is also formal.
Anna,
Yes.
what you mean by split?
Splitting means that J plus and J minus commute. So it's called also split because if you take J plus, J minus, okay, the product, you do the square, this gives identity. So you have a splitting on the tangent bundle. You have an involution of the tangent bundle.
Okay.
Is okay?
Yes, yes. Thanks.
And at the beginning, we were thinking, okay, this is the only case that is possible. No, we have this example which are not split. Now I will, if you give me 1 minute, I will tell you how this example come. Okay, it's very strange because they come from some more general stuff. Let's take a free torus, the standard free torus. We coordinate x1, x2 is free. And let's take these bases. These bases look very strange. You see why she's looking these bases anyway, but is giving new example and include all no, in fact, example of some manifold that type. So we have function that using this function, and suppose that you have you take a basis, okay, vector field depending on T, let's say the dual basis, and let's impose this condition that this essentially give that is a basis, that B squared plus B free square is non-zero. Okay, now we define two quantities. These are a bit mysterious, but are not so mysterious because if you want something, we'll take a mapping torus. So we take an action, and we need that some geometric structure is going to the quotient, essentially. What we'll consider is on the free torus a one-parameter family of almost contact metric, which are normal. Denote. So the quantity that I denoted before essentially is a quantity involving the fundamental form of this almost contact metric structure. The first thing that we show is that the inner surface you can get as a mapping torus, essentially. That's the starting of the stuff, essentially. Because if we have a diffeomorphism of the free torus, which is as a nice behavior with respect such basis. And then you have this extra condition that is essentially a condition on matching the stuff, the previous form there. Then you have the inner surface with a split generalized scalar structure. Now you can do the same play. Just take T3, take the product with the compact scalar, or compact hyperkähler manifold, and work with a diffeomorphism such that you have the previous condition combined with a diffeomorphism of your Kähler or hyperkähler map. The mapping torus that you get is something which has a generalized scalar structure, and it is split or not split depending if you are taking a Kähler or hyperkähler metric. Here, the diffeomorphism is preserving not only the compact structure, but also the method. You can see the difference from the construction at the beginning, where it was only holomorphic structure. And then we show essentially that the no-Sol manifold example are included in this construction. They are non-Kähler, they are formal. And if you start with K-free surface, you get new examples which are not Sol manifold. And I think it's enough. I close here. And sorry for some minute of delay. Thank you very much for the attention.
Thank you.
Thank you. Sorry, I am always late.
Okay. Are there questions for Anna?
One question, Anna, about this Kummer surface that
Yes.
what we discovered. What do you know about the topology of that manifold?
Okay, the manifold is, the topology is described for the special case of Kummer, and I think many results can be generalized in, for, instead of taking Kummer, taking Killer, is described in this paper by Wing and Wang, whatever, because essentially you can compute the cohomology. This is what they did implicitly, using the fact that you have something which is a mapping torus times S1. Okay, so everything can be described that. So they really show, for instance, they show that it's non-Kerr computing, even checking not only, as far as I remember, they compute the minimal model of the cohomology, for instance. They really describe everything about the cohomology.
But this manifold A of Kummer cannot be a submanifold, for instance.
No, because it's, you can distinguish from the fundamental group.
Okay.
Yes.
Okay.
Yeah. I mean, the case for the Sol manifold, as I say, if you apply what we did with Grancherov and Misha Verbitsky, starting with the 4 torus.
Okay.
So if you take the 4 torus and you take, but if you start with Kummer, you never get Sol manifold, right?
Okay, thank you.
Welcome.
Are there any other questions?
At some point, you mentioned that some example was homogeneous. Can you come back?
Yes, the example which is a steno-Kerr.
But compact homogeneous?
Yes. Is
You remember?
this was an example in this paper about a steno-Kerr on fibration, and the example is SU5 over T2, if I remember correctly. Anyway, this was but this is balance and not SKT, of course, is 12-dimensional, the example, and is balance and a steno-Kerr.
SU5 over?
It was SU5 over, if I remember well, T2. Let me check again. I want just to be sure not to say. Yeah. It's simply connected. It's simply connected. The same, you can construct also another example, but we need manifold. But again, the dimension is at least 12 as far as I remember. Yes. I can tell you the reference exactly where we show that. Is in this paper with Grancherov and Luigi and these international mathematical research notices.
Okay.
We study there the existence of this steno-Kerr structure.
Okay.
Yeah.
Thanks.
I can send you exactly the reference. There is a bit more because we look there on these are non-Kerr one space. Okay? So you have this invariant volume form, whatever. And we study the condition for a one space to be balanced. And we show that this is equivalent to ask the C1, the first chain class, is non-zero. So is one of the one space, non-Kerr C spaces. Yeah.
Okay. But maybe 11 dimension complex, right?
Yes.
Okay.
Very big. It is one of the examples. You can have more, but yeah, there we wanted just to construct. Essentially, there was a question by Tosatieva and Zekaledi. This was a question: why you need this metric on the same complex manifold? You have a metric which is balanced and a steno-Kerr is related to a problem related to complex Monge-Ampere equation, essentially.
Okay.
And this problem is a problem where you have, let's say, you fix a metric and then you consider this equation in relation with volume in relation to that metric. And so let's say the method that they were fixing was a metric which is a Stenokeller, or on the other way around because it's equivalent. That's why we looked at. Yeah.
Any other question? Okay, if not, we thank Anna again.
Okay. Thank you. So the registration is finished. Yes.
I will stop the record.